Okay, so the last video has to do with now the second class of reaction in this chapter, known as acid-base reactions. Okay, I think we've all heard of the term acid in just in everyday life. Acid-base refers to base is actually the opposite of acid, and I'll show you this a bit right now. So first, I want to kind of demonstrate this by way of example. Let's take a compound known as hydrogen chloride, HCl. HCl exists as a gas in its compound, and it is it's a nasty gas, and you'll see why in a second. If we were to take HCl gas and pump it through a beaker, I don't know, let's imagine that the beaker had a nice little hole in here, and we kind of pumped in HCl gas into this beaker full of water. What would happen is that the HCl would dissolve in the water, very similar to the way NaCl dissolves in the water. It would end up becoming a little bit of H plus and a little bit of Cl minus, and of course good old water in there kind of helps out by sticking itself between these things, so the O is kind of attached or kind of joined to the H, and the Cl's are kind of attached here. They're not really attached, but they're just sort of have an affinity because of their charge. Okay, and now I'm going to erase the water again. But the HCl dissolves completely within water, and it forms something that we call hydrochloric acid. Okay. Now, the term acid refers to the fact that this mixture that we've created has an excess of hydrogen ions. In fact, a lot of times they're just called protons, because hydrogen atom that has lost its electron is nothing more than a proton. But so essentially it has these charged protons, these charged hydrogen ions floating around in excess from what you'd normally expect from just water. And I want to talk about that for a second again, and I mentioned this before, is that if we just had, before we pump this liquid in, we've got nothing but water floating around, right? But as I kind of indicated at one point, sometimes these guys kind of split, and you got a little bit of a plus, and you got a little bit of a minus floating around even inside the water. And water actually works this way. Even though you have pure water, most of the molecules in that liquid are going to be H2O molecules, but some of them have split apart the way I've kind of drawn it here. And in reality, what happens to the H is, even though we tend to draw it as an excess H plus, which is exactly what we mean by acid, extra H pluses. In reality, the H plus kind of immediately joins up with another water and truly forms what this thing, which we call H3O plus, which also has the name hydronium. Okay, all that is a more accurate depiction of what's happening inside an aqueous solution that has extra H pluses floating around. But in practice, a lot of times, we all know that this will happen, but we tend to draw it as though it really is H pluses floating around here with a little bit of OHs floating around also. Okay, but when we put in that HCl gas, now what we have is we truly have a bunch of extra H's and chloride, H positive and chloride negatives floating around, to the point where there's truly an excess of protons, of H pluses, more so than just in pure water. So this is what we actually call an acid, because it has an excess of hydrogen. Okay, I'm going to draw a different beaker now, and we're going to start with a solid known as sodium hydroxide. Okay, that's a white solid, and it dissolves freely in water. So we're going to pour this solid into our water and stir it around, and sure enough, it dissolves. It dissolves completely. And what's floating around here it's an ionic solution now, made up of sodium cations and hydroxide anions. Now again, if you remember before, water naturally kind of splits up into H's and OH's. But here, when we dissolve this in, we get an awful lot more OH's than you normally see just in pure water. This is what's known as a base. Or you could even think of it as an antacid. It's not it's an anti-acid. Meaning if there was any acid that was added to this, let's say we pumped in, boy, you wouldn't want to do this experiment at home. We pumped in a little HCl gas here. This would form a really nasty reaction. So don't ever do this. But what would happen here is as soon as the H and the Cl started to dissolve from this compound, the H would immediately gravitate towards this thing because it's like an antacid. And so it neutralizes the excess acid from this new compound. And immediately, of course, the H and the OH would just form normal water molecules, which are floating around in excess anyway. So essentially, the NaOH, the sodium hydroxide solution that we have here, this is a base. It's a basic solution, and it acts to neutralize, meaning consume extra acid solutions that would exist also. So sure enough, if you were to do this, again, you would never want to do this casually because this would generate so much heat that it might actually explode, but it would certainly get super, super hot if you actually did what I drew here. But from a reaction standpoint, we're essentially saying that NaOH and HCl, if you were to dissolve them in water, I'll erase my beaker now, would dissociate to form Na ions, OH ions, H plus ions, and chloride ions. And of course, these two guys would immediately join to form water. And a lot of heat. We'll get into that when we start talking about energy. So this is a classic acid-base reaction, which essentially takes a base, meaning something that is naturally attractive to acids, to protons, and another which is an acid, which is a supplier of protons, and they react to essentially neutralize the acid. Okay. Now, I want to talk about strong acids and strong bases as opposed to weak acids and weak bases. So the reason why both of these compounds that I chose are known as strong bases and strong acids is that they contribute, they very much want to fully contribute a hydrogen in this case, or fully contribute a hydroxide or a consumer of a hydrogen fully when dissolved in the solution. There are other acids and other bases that are known as weak acids, weak bases, because it's not such a it's not as full as this. It's probably not a great explanation. Let me give you an example. Here's a solution which is made up of sodium phosphate. Okay. Actually, do I want to use that? Sorry, I'm going to do the acid. The acid form is going to be phosphoric acid. Okay. Phosphoric acid is made by essentially dissolving this that I've drawn in water. And what you'll have is, you'll have some phosphates rolling around. And you'll have some H pluses rolling around. Right? So the way I've drawn, and remember all these guys are negative. So the way I've drawn this, you might say Well, why is that a weak acid? If anything, it looks like a stronger acid than HCl, because when you dissolve it, you've got 3 times, at a molar level anyway, 3 times as many H pluses rolling around as you do PO4, so, or as you did with HCl. So this actually, on the surface, looks like it would be a strong acid. The reason why it's not is a lot of these H's are actually kind of happy, sort of hanging out still with the negatively charged oxygens as part of phosphate. And so, yeah, you might on balance have, some of these floating around and free, but the rest of them are still sort of happy attaching itself to the anion, to the polyatomic anion, in this case phosphate. Okay, and so on balance, it doesn't produce near as many hydrogen ions as HCl does, and in HCl's case, there's not this kind of natural association back to the parent anion. In that case would be chloride. So this is a much weaker acid. Another weak acid, just to draw it, is something called carbonic acid, which we know as sparkling water. When you dissolve this, basically you dissolve it by pumping in CO2 gas. CO2 reacts with water to essentially form H2CO3 in solution, which basically kind of becomes a mixture of H and C and HCO3 minus, and maybe even H and a little bit of CO3 double minus. But also in solution is truly a little bit of COOO, that's carbonate, right, with H and H, which is essentially this in solution, meaning it's in solution and it dissolves because it likes to be around all the waters, but it isn't really that strong a supplier of excess hydrogen. It does supply it a little bit. That's why carbonated beverages have an acidic nature to it, which dissolves your teeth, among other things. But it's really a weak acid as compared to the first one we looked at. And there are other strong acids as well, besides hydrogen chloride or hydrochloric acid. For example, sulfuric acid is very strong as well, and there's a number of them listed in the book. But this is kind of why there are things like weak acids and weak bases. I haven't drawn the weak bases, but the weak bases kind of are the same sort of concept as this, which is it's kind of an attraction. It's willing to accept a proton, but not as much as just a strong base like this, sodium hydroxide. Okay, I think that's all I want to cover for this one. End of tape.